This is Ritesh Srinivasan and welcome to my channel. In this video, let's look at an interesting resource, CNN Explainer. So CNN Explainer is a tool with which you can interactively visualize and learn about convolution neural networks. Okay, here is a simple example which is shown over here, and let's go to the page, right? So there is this image of a coffee mug, and this is classified as an espresso by passing this image through a convolution neural network. And you can visualize all the different layers of the network and how certain operations are performed in this convolution neural network. Okay, so if you are the kind of the person who can read through this page and understand convolution neural networks, you can skip the rest of the video. But there are some nuances which I observed in this CNN Explainer, which I want to explain. Okay, so first question, what is a convolution neural network? Right, so convolution neural network is a neural network, basically an algorithm used to recognize patterns in data. A typical neural network consists of a collection of neurons, and it is organized into layers. Each layer has their own learnable weights and biases. Okay, and a neural network can be used to classify images, right? Can be used to perform different kind of machine learning tasks. Okay, so for a convolution neural network, how are they different? Right, so for a convolution neural network also, you have neurons, right? You have layers, but these layers are called as convolution layers. Okay, now what is a convolution operation? First, let's look at what is a convolution operation. Okay, so a convolution operation is nothing but you have an image, okay, or you have a matrix of values. It can be an image or a matrix of values. In this case, this is the coffee cup image, and your image has, it is 64 by 64 size, so it can be represented as a 64 by 64 matrix, and each value in the matrix is a pixel value, right? So the first thing to note over here is that this pixel value over here, say for example, some values over here are in the values of 0 to 1, right? Generally in a image, if it is an RGB image, you have three channels, red, green and blue, and each pixel will be in the value from 0 to 255, right? What is done over here is that you are converting each pixel value in the range from 0 to 1 by, how it is done is that you divide that pixel value by 255, okay, and you get a value, right? So that is what is done over here. Okay, now here you see this 3 by 3 matrix, right? This is called as a kernel, and these are the values in the kernel, minus 0.25, minus 0.22, 0.01. Okay, these are weights of this kernel. So you have an image, you have an kernel, right? Now what is convolution operation? Convolution operation is you apply this 3 by 3 matrix over this input of 64 by 64, right? One pixel at a time. Okay, one pixel at a time. You move over this input. When you are moving this 3 by 3 matrix over this input, what you are computing is that you just place this 3 by 3 pixel on top of this value, right, over here on the image. So you will get 3 by 3 is your kernel. So you are looking at 9 pixels over here. So the 9 pixels have their values, right? What you do is that you take that pixel value and multiply it with the weight value. It's a dot product. And then you sum it up. You get a value. That is the output value of the convolution operation. So once this particular kernel is applied over this image, right, you get this output. Okay, so this is a convolution operation, and this 3 by 3 matrix is called as a kernel or a filter. Okay, so why is it known as a filter? In classical image processing, you have certain values of this matrix, right? And when you apply over this image, it can detect edges. Okay, so it was kind of filtering on the image. So that is where the filters term kind of comes. Okay, so this is the convolution operation. So once this operation is done, then there is an activation which is happening on this. Okay, so here what happens is that if you look at this example over here, you have an input image, right, which has been normalized. You have your red channel, green channel and blue channel. Now if you click on the image over here, the convolution operation over here, right, what happens is that, as I said, a kernel is applied on this image. Okay, now you can look at that operation also. So this is the kernel 0.3, 0.21, 0.007, 0.19, 0.1. This is the 3x3 kernel, right, which is applied over this image, and you get an output. This is an intermediate output, okay, to which a bias is added. To all the values, a bias is added over here, right? So in this case, in the first layer, what is happening is that here they have considered 10 filters. So there are 10 different kernels. So there are 10 different matrices, like 3x3 matrices with different values. Okay, and these values can be learnt during the training process. So these 10 values, right, basically 10 filters are there. Now each filter is applied on all 3 channels. Okay, red, blue, RGB, basically red, green, blue, right? And when you apply a kernel on this image, in the green channel, in the red channel, you get one output. In the green channel, you get another output. In the blue channel, you get another output. Okay, then you sum it up, and that is how you get the first filter's output. Okay, first kernel's output. Take the second kernel. Okay, repeat the same operation. Okay, now I'll come out of this. Take the second kernel, repeat the same operation, and that is how you get the intermediate output of the convolution layer. Okay, you add all the intermediate results over here. Intermediate result is nothing but applying a kernel on a certain channel. Okay, in the red channel. Again, this is an intermediate on green channel, intermediate on blue channel. Sum it up, add bias, you get your first convolution output for the second filter, and so on for the 10 filters over here. Okay, how many intermediate results do you have? You have 3 intermediate results because of 3 channels, right? And you have 10 filters. So you have 3 into 10 intermediate results. Okay, but when you sum it up, you get 10 results over here, convolution results. Okay, so that is about the convolution layer and the convolution operation. But there are some more nuances to the convolution operation. Let's go to that. That is also very nicely explained over here. Okay, so as I said, kernel. Okay, so we can consider a smaller kernel like a 2x2 kernel. So if you look at this 2x2 kernel in this input of size 5x5, it looks at a smaller area, right? It looks at 4 pixels. Okay, if I were to increase it to 4x4, right, what happens? It looks at 16 pixels. What is the intuition over here? If you have a smaller kernel, it can look at local features. If you have a larger kernel, it can look at global features. Okay, one thing. Next thing is, what is padding? Okay, so if you look at how kernels are applied, it is applied like this, right? 2x2, it starts from here, right? Now what if you want to look at the borders? Okay, what if you want to give importance to this pixel alone? Okay, that means you have to apply the kernel outside of this image, right? That is where you can add borders, that is padding. So the moment you did padding of 1, you see that it has added these extra rows and columns, right? Borders basically around the image. And one of the way of doing padding is by putting these values as zeros. That is called as zero padding. Now what does this help in? Okay, without padding, if you were to look at when the filters are applied, your input is reduced over here, right? Why is this reduced? Because simple, you are applying this 4x4 matrix over here to the pixels, right? And you are getting one output over here. Another next 4x4, next output, next 4x4, next output, next 4x4, next output. So one row is reduced to, a row is reduced, the number of columns is reduced over here, right? You have 5x5 as input, your output is 4x4. You get this by doing this set of operations. So once you finish the first row, then you will go to the second row, right? 1 by 1, third row 1 by 1, fourth row 1 by 1. That is how you get this output. Okay, now there is also one more parameter called stride. Okay, what is stride now? Okay, in this case you are moving pixel by pixel. Okay, what if you want to move by 2 pixels at a time? Okay, so that is where stride will come. Now I have moved to 2 pixels, right? So when I increase stride to 2 over here, right, and then okay, I also make padding. Okay, So now for some reason it's not working. Maybe. Okay, so now if you see, I want to reduce the this thing and maybe a stride of 2. Okay, now it works. I don't know, there was some issue why it was not working. Now you are seeing that there is something called stride, right? Now just observe how the kernel moves. Okay, so this is the first one. If you see the next one, it is moving by 2 pixels. Okay, first pixel, it is directly jumping to the third pixel and so on. Okay, when you are increasing this stride, what happens is that your output is reduced, right? What happens is that it kind of reduces your input space, right? It was a 6 by 6 input space, your output is now 3 by 3, right? It is kind of a reduction. Okay, so that is about stride. Okay, but in this particular architecture, which they call it as tiny VGG over here, the stride is 1. Okay, so this is about the convolution operation, and its hyperparameters are input size, which is your input of your matrix, then you have padding, you have kernel size, and then you have a stride. Okay, so if I were to reduce the input size, and this stride is not feasible, that is what it says over here. Now why is that stride not feasible? There is a certain computation on the output. Okay, now how do you actually compute the output over here, right? Why is it 4 by 4 given this input of 5 by 5? Okay, if I were to increase the kernel size, what is the output? Okay, and if I were to do some padding, right, and again increase the kernel size, right, maybe I do I increase the input size, I also do a stride. Okay, now you see that input was 6 by 6, the output is 3 by 3. So what is this formula? Using these parameters, how do you compute the output? Okay, the simple formula for a square image where width and height are same is this. Okay, you can compute the output using this formula where W stands for width of the input, right? K stands for the kernel size, P is your padding, okay, and S is your stride. Basically you compute this W minus K plus 2P divided by S, floor of that value plus 1. Okay, so if you were to go over here, your input size is 6 width, right? Your kernel size is 4, right? So 6 minus 4, which is 2. Your padding is 1. So 2 plus 2 is how much? 2 plus 2 is 4. Right? Using this formula, padding is 1. Kernel width was 6. Kernel was 4. So 6 minus 4 is 2. 2 plus 2, because padding is 1. So 4 divided by stride is 2. So 4 divided by 2 is 2 plus 1 is 3. That is how you are getting this output is equal to 3. Okay. In most of the cases, you will consider a square matrix. Okay. Because of which this formula can be used. Now, assuming that you are, it is a non-square matrix, something like your input is 7 into 6. Okay. Then what you can do is that you can apply the same formula, to calculate the output size, where W, instead of W, in one you use H, height, in another one you use width. So you will get different, for the different dimensions, you will get different values of the output. Okay, so this is a very important formula, a typical interview question where they ask you this thing, like given an input parameters, calculate the output of a convolution. Alright, so this is the formula, W minus K plus 2P divided by S plus 1, floor of this plus 1. Okay, so now you are clear with what is a convolution operation and how convolution is done on a input. Right, the next is activation. Alright, so why do you need to do activation? It's basically you want to introduce some non-linearity, right? Because this was linear computation of features, right? You want to introduce non-linearity. Okay, so for that, if you go over here, they have applied something called as an ReLU activation function. What does the ReLU activation function do? It takes every value and it computes a max between that value and 0. So if it is a negative value, it will come as a negative. If it is a positive value above 0, it will come as that positive value. That is how non-linearity is introduced over here. Okay, that is using your ReLU function. Okay, now let's go to ReLU function. This is the definition of ReLU function. ReLU of any input x is nothing but max of 0 comma x. So for the negative values it is 0, for the positive values it is that positive value. So that is what is applied over here. Okay, so this is the activation function. Okay, so now if you look at the first layer, a convolution operation has been applied with 10 filters. You get 10 convolution outputs for each of these 3 channels. So basically convolution operation is applied on each channel and the values are summed up for each filter and you get 10 such values. ReLU is applied on this convolution output. This is the output of your first layer in this convolution neural network. Now you can introduce an additional layer over here, a second layer, third layer and so on. So if you look at the second layer, it will take as input, again 10 filters are applied, right? What it will do is that if you were to go and look at what is the convolution operation which is happening over here is that your kernel is again applied to these 10 outputs of the first layer. They are summed up, right? You get the intermediate values, they are summed up, okay? And this is done for all 10 different filters, right? And they are summed up and you get 10 outputs over here, the convolution outputs. Okay, so I'll go out of this, and if you were to look at the second one, right, again the same process happens. So this is the second convolution output. Okay, right? So now ReLU is again applied, right? So you have 10 different outputs over here, right? And then an operation called max pooling is done. Now what is this max pool operation? Okay, that's also explained in detail over here. Let's go to max pool operation. So those layers are called as pooling layers. Okay, so what does pooling layers help in? They help in gradually decreasing the spatial extent of the network, which reduces the parameters and overall computation of the network. So in this particular architecture, they have used something called as max pooling. It requires selecting a kernel size and a stride length during architecture design. Once selected, the operation slides the kernel with the specified stride over the input while only selecting the largest value of each kernel slice to yield the value of the output. Okay, so here they have used a 2x2 kernel and a stride of 2. Now let's look at what is max pooling. Okay, so if you go over here and you click over here, it shows what is max pooling. So this is a 2x2 kernel. It is just basically it slides over this image, and for this 2x2 neighborhood it just takes a maximum value. Okay, for example over here it takes this maximum value of 0.11. You go to the next one, it takes a value of 0.1 and so on. So this is max pooling, and if you this is using a 2x2 this thing with a stride of 2. Okay, so whenever you use stride values greater than 1, you get a reduction in your input. So you see over here you get this reduction again from 60/60 into 30/30. So this you can consider some kind of feature selection of which is happening over here, whereby max values in your input are taken and your input spatial resolution is reduced over here. So basically you start with the big image, right, and slowly you are reducing your feature space, okay, as you go deeper into the network. Okay, there are convolution networks where you first do downsampling like this and then again you can increase the resolution also. Okay, but in this convolution network, if you look at it, you start with a 60/64 input, and if you look at towards the last max pooling, it becomes 13/13. Right, it is kind of downscaling of your input space by performing these convolution operations and max pooling operations. So this max pooling happens over here and you get the output of the layer, the second layer, and then it is given as input to the next convolution layer. Okay, this is again a convolution and ReLU operation which happens, followed by again a convolution, ReLU and max pooling. Okay, so you have how many layers over here? You have a convolution layer, activation, convolution activation, max pooling, convolution activation, max pooling, right? So after this layer there is directly the output, right? So why does this output come? Okay, let's go to that also. So max pooling operation was done over here, and here if you see that there is something called flattening which is happening, right? Now what is flattening? Okay, that is also explained over here. What is actually a flattened layer? Okay, So a flattened layer converts a 3-dimensional layer in the network into a 1-dimensional vector to fit the input of a fully connected layer for classification. So if you have a 5 into 5 into 2 tensor, it becomes, a vector of size 50. 5 into 5 is 25, 25 into 2 is 50. It becomes a vector of size 50. The previous convolution layer of the network has extracted features from the input image, but now it is time to classify the features. Okay. So if you were to look at over here, till this point feature extraction was happening. Now you got the features. And now you want to classify these features. Okay, that is what this flattening is happening. And you have a single feed forward network over here where this flattening is happening, and this flattened vector will be given as an input to that single feed forward, basically single layer, and then you will do some computation to get the output. How does the classification now happen? Right? For that, we use something called as Softmax activation in this particular layer. In the final layer, you use something called as Softmax activation. Now, what is Softmax activation? Okay. So if you see over here, our input image was coffee cup, right? It should be classified as espresso. Okay. So how does it happen is that you have 10 output neurons. Okay. To which input is coming from your flattened layer. Okay, for example, one input is this, one more input is this, one more input is this, and so on. Right? Flattening happens and that flattened input is given. Right? Then what happens over here is that you basically sum up the vectors over here with the weights of this layer. Right? And basically that summing up happens and a bias is also added. You get a value. Okay. For example, that value is, say for espresso in this particular neuron, that value was 8.65. Okay, what you do is that you apply exponential to that value and you divide that by sum of exponentials of each of the other neurons along with this neuron. Okay, each of the values at other neurons along with this neuron. That is what is shown over here. So what is the formula for softmax? Okay, if you have 10, in this case we had 10 neurons, right? So let's go to that softmax formula. So we had 10 neurons. Okay, so for that value of softmax at that espresso, that particular neuron is the value, xi is the value of all the values which have been summed in the previous layer, like in the previous all the values which have been summed over here, this summation from the different like outputs of the previous single flattened layer, right? That is the value x. You take exponential of that divided by all the other neurons, values of all the other neurons. Okay, that is what is this formula. Exponential of e of x divided by, sum of exponentials of all classes, of all the values of all the classes, right? And the softmax operation, it serves a key purpose because it makes the CNN output sum to 1. If you were to sum up these values of softmax across these 10 neurons, it will be equal to 1. Okay. Now, why this needs to be equal to 1? Why should it be equal to 1? That is because to train this convolution neural network, you would want to do back propagation, right? So you would want to do back propagation. That is how you train a neural network, right? So when you want to do back propagation, what you will do is that, how will you do back propagation? You know the output is espresso, so the value is 1 over here. The value which has been computed is 0.881. So 1 minus this you will do, and that is the loss which will get propagated backwards in your convolution network to actually learn the different weights across each of these layers. Okay, to learn the different weights of the kernel matrices, right, the kernel filters. So that is what will be used. Okay, so that is how you actually train a convolution neural network. So this is how a convolution neural network works end to end. That is what is been shown in this particular visualization. Okay, I suggest that you go over this visualization, you look at each layer, you try to understand the mathematical operations at each layer to get a better understanding of what is a convolution neural network, and then you can start looking at how can I code my own small convolution neural network with this understanding. I'll be posting the link to this CNN explainer along with the paper as well as this formula for computing the output of convolution. I hope you like the video. If you like the video, please like, share, subscribe to the channel. See you in another video. Happy learning.